On our practice, the flow between two rotating rings. At first we will build geometry, then mesh and make some simulation in Fluent, ANSYS Fluent. So let's begin. I will open ANSYS. ANSYS Workbench. Create new project. Using Fluid Flow Fluent. The analysis system will be Fluid Flow Fluent. Put it on the worker table. Select geometry. The first problem will be very simple. It will be 2-dimension. So I will change the analysis type from 3D to 2D. Then right click on geometry. Select new design modular geometry. The new window is opened. It's design modular for constructing the geometry of our flow. As I told you, we will study the flow between two rings. So the geometry is very simple and it consists of only two circles. Let's use XY plane. The default option units are meters. We will change meters to centimeters. So open units and change meter to centimeter. Two circles with the center in the 0 point. One will be for example 100 centimeters, and the external circle will be 150 centimeters. So open sketching. draw, and circle. The center of the circle is in the 0 point. One circle. And the external circle will be the following. As I told you, the radius of the external circle we will put 150 centimeters. So open the dimensions. Radius. And select external circle. One, 5, 0, 100 and 150 centimeters. And the internal circle, the radius is 100 centimeters. Now we will build, using these two circles, the flow region. So return to modeling, select sketch 1, concept, and the option surfaces from sketches. We will build surface from these two circles. The base object is sketch 1, so click apply, sketch 1. And other options are, we will use the default options, add material, and so on. Then click generate. So we have built the flow region, which is located between two rings, between two circles. Let's save the project. I create new folder, which I will name two rings open this folder, and the name of the file project simply 1. OK. Now I can close the geometry, the design modeler. Close. And let's start the second part of our job, building the mesh for this very simple problem. So open mesh. The first operation is creating named selections. The named selections will be used for constructions for setting boundary conditions. We have only two geometry parts, the internal circle and external circle. Change selecting face to selecting edges. This button. Now click the internal circle, right button, and select Create Named Selection. This region will be called int ring. Internal ring. Okay. And now external ring. Click on this edge, right click, create named selection, Ext ring, external ring. Okay. Now let's create the first very rough, very coarse ring mesh. So generate mesh button. Very coarse, so let's improve this mesh. For this purpose we will click mesh, right button click, insert, I think maybe sizing. Let's try it first, this. For setting sizes, at first we must select the geometry. We want select the edges, external and internal. So I click on internal circle, then on external with a control button. So two geometry edges are selected now, and then apply. You see that in geometry we selected two edges, external and internal rings. Then the definition suppressed will change to no. Oh, it's no, it's okay. No. Then the type, it's better to use something like number of divisions. It's better to use it. And for example, for the first attempt, use 100 divisions. Okay. The behavior, it's better to change to hard, but let's try to rebuild our mesh using soft behavior. For updating mesh, we must click mesh and update option. Now I think the mesh is much better than it was before, but we will improve it more. First of all, let's look what is hard or soft behavior. So again, open edge sizing. Behavior, let's change to hard. And again, update mesh. I think nothing has changed. A little bit better, but we will improve it again. For this purpose, use again some options in the mesh construction. Right click mesh, insert, face meshing. In this case, we must use the whole geometry. So the option is face. We must select face. Click on the face of our geometry and apply. Method. The method is quads. It's okay. Again, update mesh. Well, now we have very good regular mesh. But I think that for better results we must use more fine mesh. So I will change edge sizing. Instead of 100 divisions, let's try 200. Again, update mesh. Update. Not so bad, but again, I think I can change it even twice. Edge sizing, instead of 200, 400. And again, update mesh. Very fine mesh is created. I think it's okay. We will save the project. I don't know why. Let me see. Oh, it's okay. So I think everything is finished with mesh building. The mesh is very simple and I hope fine enough for our problem. Close the mesh window. And let's start the setup of geometry of our problem. I think we will not change anything in optional parameters. Okay. Okay, we have pressure-based type of solver. Default type is okay. Velocity absolute. Steady problem. And 2D space is planar, not axisymmetrical. Let's check our mesh at first. It's useful option. No errors. Units are default values. Okay. And now let's go on with models. First of all, the energy. Let's switch on the energy equation. Okay. Viscous. I think the flow will be turbulent, so I will change the model from laminar to K epsilon. And at first we will use standard K epsilon model. Maybe next time we will try another turbulence model and compare the results. Okay. The other options for the first calculation are not changed. Default material is fluid air. Let's try, instead of air, liquid water. Click, for this purpose, let's click fluid, new, and open the Fluent database. Here we have a lot of fluids, some of them liquid, some of them gaseous. We want water. Oh yes, water liquid, not water vapor. Select water liquid and copy it to our new fluid. Now close. Now we created new material which is called water liquid. The chemical formula is H2O. The properties: the density constant, the specific heat is also constant, and the same for conductivity and viscosity. For our problem it's okay. Now click Change Create button and close the window. Now we have this liquid. Next, cell zone conditions. Double click cell zone conditions. Operating conditions. The operating pressure, which we can call reference pressure, is about 1 atmosphere. Okay, it's okay for us. Then it's very important to get the information about the main parameters in the flow. Edit. You see that by default the material name is air, but we want to use liquid water, so let's change the material to water liquid. Now okay. I think the cell zone conditions are ready. And now this next step of our problem is setting the boundary conditions. We want to have two rotating rings. So let's start. We have an external ring and internal ring. One ring will rotate clockwise and the other to the other direction, anti-clockwise. Let's start from external ring. The type is wall, it's okay. The type of boundary. Now edit. The first page is momentum. By default, wall motion is stationary wall. We will change it to moving wall. Shear condition no slip. It's okay. Relative to cell zone, let's change it to absolute. And the direction, not translational, but rotational. The axis of rotation is 0 point, so the coordinates are 0, 0. Let's use the anti-clockwise direction. It's positive value, and you see the speed is radians per second, and we'll use something about 50 radians per second for external ring. The temperature of the wall now. We don't want to use heat flux, we will use the temperature of the wall, so select temperature and 300 by default, it's okay, let it be so. Okay. Now the internal ring, the same type, wall. Open this. Also wall motion will change to moving wall. No slip, absolute, rotational, around 0 point. And now we will use clockwise direction. It's minus value. The same but in the opposite direction. Minus 50 radians per second. And let's make this wall having temperature more than the temperature of the external ring. So the temperature the liquid water, of course, should not be more than 100 Celsius. So 350 Kelvin degrees. Okay, so the temperature is 350. Okay. No other boundary conditions. The solution method is fully coupled. Monitors residual. The residuals for continuity and momentum equations are about 1 per 1000, and for energy is much more. Let's change the residual for momentum equation to these values: 0.3001, 1 to 10,000. The other absolute criteria for residuals are the same as default. Okay. The next step, initialization. Open it. Let's try hybrid initialization. So I clicked the initialize button, and the last option is run calculation. We will not change anything on this besides the number of iterations. I think 300 iterations will be enough. and click Calculate. I don't think that the calculation is completed as for the residuals, but let's look at the results. So open the result. I will close the models. Set up and open the results. At first, graphics and contours. Double click contours. What is interest for us is the velocity. The velocity value in x direction, x velocity. Save and display. We see that near the external ring, the velocity is directed anti-clockwise. The negative value in the upper part of boundary and positive value about 75 meters per second near the bottom side of our ring, and near the internal ring we have the direction clockwise. Here is positive value, and the bottom negative value. So I think it's okay. The y velocity is also shows us the same result. So near the external wall the flow rotates anti-clockwise, and near the internal ring the direction is clockwise. What we can examine next: velocity, for example. Radial velocity. The same result. Now temperature. You remember that the Temperature of internal ring is 350 degrees Kelvin. The water is near this wall is warm, and near the external ring we have the cold water, about 300 degrees. But the main flow has something between these values, about 320, 330 degrees Kelvin. Close the contours. What we can maybe pass lines. I think we will not get anything because we have no particles, so I have problem with program. Have to close the program. It's because there is no particles, of course, in our task. Again, open the setup. I'm afraid I'll have to repeat the calculation. Yes, I have no calculation. I have to repeat it. Boundary conditions. Internal edit. Boundary conditions have been saved. So again, run calculation. We repeated this step. Let's look again on contours. temperature, static temperature. Yeah, the same result. Okay. What we should do now? I want to build the radial distribution of the plot with radial distribution of some parameters. For this purpose, close solution, setup, parameters, custom field function new. Oh no, it's not. User defined function, no. Yes, let's build the special surface. In this case, not surface, but line. So results surface, new line. I want to build the line between two circles. For example, in this place, it's parallel to the x-axis. So the first point has, you remember that we have 100 centimeters, so it's 1 meter. The x direction is this point. The y is 0. And the second point has 1.5 meters in x direction and 0 y direction. It will be these 2 points. Let's use the default name line 4. Create. Close. Now let's open plots. XY plot. And use this new line 4, for constructing a new plot on this line. At first, velocity. We are interested in y velocity. Save and plot. Very good. Near the walls in the boundary layer, it's near the internal wall. It had the negative value. And the positive value of y velocity is near the external ring. The position 1 meter and 4 meters. What about the temperature? Yes, we also have the hot wall and hot temperature near the internal wall and cold water, better to say colder water, near the external wall. Density is constant pressure. The relative pressure is increasing to the external part. That's right. And what about turbulence? Turbulent kinetic energy is increasing near the walls. Turbulent viscosity, effective viscosity, better turbulent viscosity. Has the biggest value in the middle between the rings. Close it. And now let's try to change the boundary conditions at first. Let's change the rotating velocities. Decrease it. Next ring. We used 50 radians per second. Let's change it to, for example, 20 radians. Okay. And the same, but in the opposite direction for int ring. Minus 50 will change to minus 20 radians per second. The other values are the same. Okay. And new calculation. I will make 500 iteration. Okay. I see. Okay, and let's compare the results. Close setup, close solution, results, XY plot. At first, velocity. Y velocity. Okay. The picture is very much like the previous case. Also the boundary layer, narrow boundary layer, and slow variation of velocity in the middle of the flow. I will try to use the other turbulence model. Maybe the plot will be changed. Let's save the picture. I prefer PNG format. Save. Two rings. And the picture is called velocity V, and the model, the name of the turbulence model, V K E. Okay. Let me see. Two rings. Yes, I have saved the picture. It's the velocity, the radial velocity, not radial, but y velocity, in case when we are using K epsilon model for turbulence. Let's change. Let's use another turbulence model. So setup, models, viscous, standard K epsilon. We will change, for example, to K omega model. The most widely used K omega model is SST. Let's use it. SST is shear stress transfer. Okay. Now solution. Run calculation and calculate. Okay. We used the previous results as the initial conditions for this simulation. Let's compare the results. So results, XY plot, and we open the same picture. And I think the result is very much like with K-epsilon model. So again, save picture. Save. V, and instead of K epsilon, SST. Okay. I think the results are very much alike each other. It means that let's use, we have some time, I will use one more turbulence model to compare. If we again get the same result for velocity, I think that the results are okay. The different turbulence model gave the same result, and it's okay for our calculation. So setup, models, viscous, and I will use more complicated model, which is called Raynaud stress. The default linear pressure strain. All model constants are default, so okay. It's better to initialize this again. So before solution, before calculating, I will initialize the calculation. Solution initialization, hybrid initialization, and click initialize. Okay. Then to go back to run calculation, change nothing, and click calculate. We have some additional equations for turbulence. So we have a lot of equations, and the solution is slower. But not very much. I'm afraid the result will not be satisfactory. But we will see. At first I will look at the contours in this case. Open the results, contours, and the same contours as before, the temperature. It looks like the previous results. And what about the turbulence? Turbulent kinetic energy. I'm afraid that the result is not very good. Reynolds stress UU VV VV The turbulence parameters are very strange. I think that in order to improve the results, we must make the boundary layer, the mesh near the boundaries, near the walls, should be finer. The sizes of the mesh near the wall should be much smaller in order to get satisfactory result. And the dissipation, but let's build the plot. So results XY plot and the same plot as before. Velocity, Y velocity, safe plot. I don't think that this result is good. So for this case, the complicated Reynolds stress turbulence model gave us a better result for this calculation. Maybe I will try to improve this situation. Set up models, viscous, maybe better to use not linear pressure strain but stress BSL. Okay, and run calculation. Oh yes, the results are a little bit better than when you use standard model. better but not perfect. You see, the residuals are increasing and very big, about 100, the minimum value of Renner stress equations. Just one more time. Results, XY plot. Y velocity, save and plot. No, it's not good, but let's save this picture. The same V velocity, Renner stress, RS, BSL. We use the modification BSL. Okay. The result is very much differs from the previous results. So I think that the Renner stress model is not okay for our solution. In order to improve the result, as I told you, we must use the fine grid or mesh near the walls. So I think for this lesson it's enough. Let's finish the practical lesson. Save the project.